Hello and welcome to this manufacturing process technology module 2, part 2, module 31. We were actually discussing about EDM circuits, and in context of that we mentioned about the famous resistance capacitance circuit which is used for feeding power to any EDM system. So in context of that we were trying to look at the maximum power transfer which happens in such a circuit, and we found out the total power that is delivered to the discharging circuit would really be the product VCT times of ICT, and we already know that VCT can be represented in terms of V0 1 minus e to the power of minus t by RC C, and ICT can further be represented as V0 by RC times of e to the power of minus t by RC times of C. The total energy DEN would actually be a product PDT in this particular case, because obviously power multiplied by time gives the total energy which is transferred. So here we would like to have the total energy transferred to the discharging side as a product as written here times of dt, where dt is the elemental time for which the power is being transferred. So if we integrate this on both sides, we are left with the value of En, which is V0 square by RC times of minus tau e to the power of minus t by tau plus tau by 2 e to the power of minus 2t by tau plus K2, where K2 is the constant of integration, and we have assumed this RC times of C to be the time constant tau which we are just simply replacing here in all these terms just for brevity sake in the way we are representing the formulation of the equation. So let us now try to evaluate what this K2 is. So at time t equal to 0, we know that the total energy that is delivered from the charging to the discharging side is 0, because it is still not hit the point when there is going to be a discharge between the anode and the cathode. So, so therefore if we put or evaluate this equation 1, let us say, under this boundary at time t 0, En is 0, we get the value of K2 to be equal to V0 square tau by twice RC. So as you know, this term will go off, so will this, and we are only left with minus tau plus tau by 2. This is 1, this is 1, this is 1 at t equal to 0. So you are left with only V0 square tau by twice RC as the K0. So if I substitute this back into this equation here, right here, the En final formulation can be written down as V0 square by tau into RC times of 1/2 plus half e to the power of minus twice t by tau minus e to the power of minus t by tau. So that is going to be the total energy transfer between the input circuit or the discharging or the charging circuit and the discharging circuit. So if we look at now what is going to be the average power to be transferred, so we have to really concentrate on the the charging time and the time for which the energy is being discharged. So let us suppose that Tc is the time for which the energy En is delivered to the discharging circuit, the condition of maximum power can be arrived at by simply differentiating the average power, which I will just calculate in the next step, okay, divided by some variable here which I am going to map, okay. And let us now look at first of all what is this average power and what are the variables. So average power is nothing but the amount of energy which has been discharged into the gap by the discharging circuit per unit the time for which the energy En is delivered to the discharging circuit. So let us consider that time to be Tc, the time that it takes to discharge the tool completely, and so this also can be considered as a spark time for a single spark event. And if I were to consider, by substituting the value of Tc in the expression, we have now the En value from the last step, borrowed from the last step, as V0 square tau by Rc times of half plus 1/2 e to the power of minus twice. Now we put the value of t equal to Tc here, the amount of time it takes for the whole discharge process to complete. So you have 2 tau c by tau, okay, minus of e to the power of minus again tau c by tau. And if I were to again use the value of, let us say, tau by tau c as some value x, okay, this is some ratio that we are assuming that the actual time constant, or how many times of the sparking time or the discharging time is really the time constant of the circuit. So this t with tau by tau c is a very, very important parameter x here. So I can convert the whole equation, the power equation or the average power equation here, as En by tau c equals V0 square divided by Rc times of, you can call this tau by tau c, En by tau c, remember, times of half plus half e to the power of minus twice tau c by tau minus of e to the power of minus tau c by tau, okay. So we consider again, the inverse of this tau c by tau to be some function y. So I have V0 square by Rc times of y times of half plus 1/2 e to the power of minus twice y minus of e to the power of minus y, and we can actually put the value of y here and equate equal to 0 for the maximum power transfer condition, okay. So if I were to calculate the d power average per unit dy and equate it to 0, we would actually end up getting a solution for the maximum power transfer condition, okay. So the condition for the maximum power to be delivered to the discharging side of the circuit for time tau c equal to t, we get dp average by dy equals 0, which actually happens, I am not going to show the calculation here, but it actually happens at a value of y equal to 1.26. So which actually corresponds to, because y here has been assumed to be a ratio of Tc by T. So this is a condition which says that the total amount of time that is needed to deliver the whole charge to the discharging side. I am going to just talk about what all components are there in this time. That should be at least equal to 1.26 times the total time constant, where there is a 63% power rise in the charging side. So this is the condition corresponding to which really the maximum maximum power transfer should take place through the EDM gap. Now let us look at what this Tc corresponds to. So obviously it is the amount of total time that is needed for the maximum power to be delivered, which would definitely include the charging time. So if I look at different components of Tc, so it would be the time to charge, so time charging, okay, plus you can say a small amount of time which is spent in the spark to happen. So the time of spark, T spark, added on to the charging time. Obviously this is much greater. So this charging time is much greater than the sparking time, because the spark is really a very short lasting momentary kind of phenomena, and we can safely neglect this sparking time and just consider Tc to be equal to the charging time of the capacitor. Okay. So if I want to do that here in this particular case, I would get a very different kind of situation. So let us say if the Tc is actually the charging time, the time in which the capacitor, let us say, charges to the full extent actually, and so I can actually get the value of Vct, which is actually the voltage across the capacitor as a function of time, and it has been earlier calculated as V0 1 minus e to the power of minus t by the time constant tau of the RC circuit. So in this case, the Vct at the point of time corresponding to t equal to Tc, let us say, or the charging time, let us say, is going to be equal to V0 1 minus e to the power of minus tau c by tau, or V0 1 minus e to the power of minus 1.26. Okay. So this corresponds to the maximum power transfer voltage of Vct or capacitor as a function of time, which is needed for the whole charge delivery to happen, which is in fact about 72% of V0. So it is 0.72 V0. So if you were to operate the circuit that was being shown earlier in one of the modules here, where this is, let us say, the V0, this is what the Vct is, and this is what the delivery side discharge voltage is. So the maximum power transfer can only happen when this guy hits about 72% of the total output, the source voltage V0. Okay. So this is a sort of a smooth operating condition that the circuit should be maintained at, typically, if you wanted maximum power to be transferred from the DC voltage source across the gap in the EDM circuit. So that's about it. So we necessarily just let us go back to the concerned slide. So thus the discharging voltage for maximum power delivery to happen is corresponding to 72% of supply voltage. So for maximum power delivery, through the gap, the breakdown voltage and the supply voltage should follow the relationship VB approximately equal to 72% of V0. So the breakdown voltage that the circuit needs to be operated as about 72% of V0. So the current in the discharge circuit if we represent the sparking resistance by, let's say, RS, would actually be equal to, let's say, ID minus dq by dt equals minus C VCT by dt. So this is how the discharge would happen, assuming that the voltage as a function of time is going down in the charging capacitor when the discharge starts to happen. And the ID can also be represented as VCT by RS, and this condition, this is while discharging, right? So this condition can only happen when dVCT by VCT equals minus T by RS times of C plus some constant of integration K3. And obviously if we assume that at time t equal to 0 the VCT value or the charging capacitor or the capacitor value is charged to some value Vc0 corresponding to time t equal to 0, we have K3 represented as ln Vc0 or Vct represented as Vc0 e to the power of minus T by Rs times of C. So that's about how you can actually represent the variation of the VCT on the discharging side. Earlier we were doing mostly on the charging side, and you can see what is the operating point of the charging capacitor where the power transfer should really be the maximum. Let's kind of plot and see if we can understand what is going on here. So here you have a output or an operational voltage of the power source V0, and we know that if we wanted to operate the charging discharging side of the circuit given here, the best idea would be to sort of go all the way up to about the value of VD, discharge voltage, to an extent of 72% of V0, and then start discharging from this level. So if I want to do it multiple times for one charging cycle, this is typically TC. We assume that the sparking time is almost insignificant in comparison to the charging time. Okay, so the charge delivery would really happen as a function of TC, and then again in each cycle it gets protruded forward by TC, so you have 2 TC, 3 TC, 4 TC, so on, and each time you having the charging discharging cycle to take place at an instance VD corresponding to 72% of the power of the input voltage V0. And also if we had to plot the VI product, which is the power would definitely be maximum at a corresponding value of the total time TC equal to about 1.26 times the time constant of the charging circuit. So this is really the operational extent up to which the circuit should be ideally operated for a maximum power transfer to take place. So we will now try to look into a little different aspect and try to actually get into a little bit of studying of the behavior more from a standpoint of the discharging side behavior, and then maybe do some numerical examples where we can try to see if all these concepts together can be utilized for looking at material removal rate. So again, going back to the ID value, the discharge current value, the ID was given as VCT by RS, or in other words it was taken as VC0 by RS e to the power of minus T by RS times of C from the last step. So if we look at the energy dissipated across the IG, the inter-electrode gap, that would be given by WT equal to half CVV square, where again VB is the breakdown voltage as VCT is already known to be V0 1 minus e to the power of minus T by RC times C. So we can find out the value of the spark frequency or the total charging time from this expression right here. The total time that is sort of needed in this case for the VCT to reach its value from the output power value V0 from 0 to VCT as the output power is V0. This time is given by, again, just algebraically changing this equation. So it's RC times C ln 1 divided by 1 minus VCT by V0. Okay, obviously VCT by V0 and 1 minus VCT by V0 can be e to the power of minus T by RCC, and so you can take natural logs on both sides and this gives you the time. So from this we can actually have an idea of the sparking frequency, because obviously as you have found in the earlier trend that the signal goes all the way up to 72% of VO or the source voltage, and then falls down, and the falling down of the sparking time is very short in comparison to the charging time. So most of the total duration of sparking is covered with the charging time, and there is very less value as such that the sparking process itself adds to the overall time value. So the TC can really be estimated through this whatever operational voltage you actually operate the circuit in, and the sparking frequency then FC would actually be 1 by TC, which is actually 1 by RCC times of, again, 1 divided by ln of this whole term, 1 divided by 1 minus VCT by V0. So that's about what the sparking frequency is going to be in this particular case. So the minimum value of resistance, particularly this resistance RC, needs to be maintained so that the circuit doesn't cause an arcing like behavior, and it should limit itself to only the sparking behavior. So this is known as the critical resistance. Okay, this is the critical resistance, and it actually helps in preventing arcing for long durations to happen. So obviously if the RC were 0 in the expression here, if I just were to look at this particular expression, and if RC were 0, so it would be almost a indefinite spark frequency, or very large frequency, which would be considered as a, theoretically it would be considered as a continuous spark for a long time. So that becomes essentially arc. And that we want to avoid in this situation. So therefore, there has to be some value of RC, critical value of RC, which is non-zero, and obviously the critical value is driven by some guidelines as any other process. And if we had some inductance in the discharging side, which is otherwise given normally to avoid any kind of surge effects on the power supply here. So at least the minimum value of resistance should be given by root of L by C. I am not going to get into why this would be the critical value at which you should operate, but it has been found out that if you operate at the root over inductance per unit the capacitance here C value, and that is going to be your minimum resistance, it is going to prevent the frequency infinite condition, you know, to arrive at. So frequency infinite means very less gap between the switch on and switch off time, and it means continuity, or it means arcing rather than sparking. So we have to be careful about placing our RC in the circuit in a manner so that it is at least root over whatever is the inductance in the discharge side, which is otherwise given because you want a surge protection to happen. Typically you could give an inductance you know, in this particular region so that there is a you know, surge voltage protection of at least the power source to happen when there is a sparking condition created. So if such an inductance is there in the circuit, it is easy to design what is going to be the minimum thresholding resistance to prevent this condition of arcing from happening. We don't want an arc in EDM for many reasons. One of them is that we need the whole machining the whole surface to be machined, and an arc at one point would really create a pitting, or it would create machining at only one place, and typically the criteria of a spark dancing all around the surface, which would create uniform wear of the surface, will not be happening, or it will be prevented. Okay, so which loses the essence of the whole machining process. So today we are going to just stop at this level, but in the next class we are going to sort of module, we are going to take up that this energy given at a certain rate would really be the amount of power that is going to do the material removal, and there are empirical relationships of power with respect to the material removal through which we will try to predict some of the material removal rates that would come. So typically now if you change your circuit design, you could actually influence the material removal rate in terms of power, etc., which is being delivered, and it a lot depends on what is the dielectric fluid and what are also going to be the electrodes like the tool and the workpiece. So we'll finish this module here and look forward to doing some material removal rate calculations in the next module. Until then, goodbye. Thank you.